Keeps going. Okay, there's like 4 sections of this, and hopefully we can plow through it so we can move on. But we have a 2-point, this is defined as a 2-point boundary value problem. Man, now I'm thinking about pottery. And that problem, as we talked about last time, was this minus second derivative of our displacement was equal to this f of x in omega, was from A to B. So second derivative of our displacement is equal to our force in omega, which exists from A to B. And so this is the main problem here. And then we have boundary conditions 1A, and that is our displacement at A is equal to 1. And I'm just making stuff up. And our displacement at B is equal to 5. Or we could have a different set, which is, UA is equal to 2, and U prime of B is equal to 2. But in general, what this is called, very high level, is the strong form. And if I mentioned that before, strong form.
I think you wrote it down, but I don't think you explained it.
So strong form is basically equal to the governing equations plus boundary conditions. The bottom line is a strong form problem, this is not the problem we're going to solve. We're going to put these things called weight functions in this to make it look a little bit different. So that way we can force relationships that we can't force in this strong form boundary value problem. So this is like another way to think of it is this is the real problem. This is the problem we would like to solve without playing a bunch of mathematical tricks and putting these weight functions, meaningless weight functions in there. I mean, they're not meaningless. You have to change equations because you can't set 1 equal to 2. We can set 1 is equal to 2 times this arbitrary weight function, and not define that weight function, right? And that's essentially what we're going to do. But this is the strong form are the governing equations plus boundary conditions. The strong form is not complete just with the governing equation, and it's not complete just with the boundary conditions. You have to have all of it to have a strong form boundary value problem. And this star means this is a well-posed boundary value problem, which means the solution is unique and is continuously dependent on, I guess the best way to describe this is time data. So the strong form is minus u double prime is equal to f in omega is equal to a to b plus boundary conditions. Okay, so this is just kind of definitions of what we are, what we're doing. So remember, try to give you some context with the strong form, because I had a really, really hard time grasping this. So we have a domain, and our domain we defined goes from x equals a to x equals b, and this domain is omega, right? And this omega equal to a to b is the domain except endpoints and this a to b right here is called an open set. So we can write that omega is equal to x a less than x less than b. Now, to try to give a little bit of, or an example of what the strong form is, what we're saying is this equation right here, this minus u double prime is equal to f. That equation is only valid in this range, right? Not the endpoints, but just in that range. So if I wanted to do a coordinate transformation, so if I wanted to map our omega a to b to let's make something up here. Phi 0 to 1, and say that this is 0 to 1, and I want to do this mapping from omega to phi. Can I state that minus double prime u equals to f? Can I state this is true in phi. Can I do that? Can I assume that is true in this other domain? This mapping right here, all I did is drew like a little arrow saying that's what I wanted to do. I didn't create a mathematical model relating those two. I didn't say that A is equal to 0 and B is equal to 1. I didn't state that. So as you know it right now, this is not true, or it's not verified. But if I were to write something silly like minus u double prime is equal to a, it's supposed to be a lowercase phi f, well, then it can be, right? Because you don't know what phi is. And this thing right here is, we're going to be calling these weight functions.
Real quick.
And then, oh, hold on. And then this would be considered a weak form. And we're going to do some examples of this, but it's not the same. Go ahead.
Oh, I just had a question about omega. So is omega supposed to be just our like geometry from one point to another point, or is it something else? Or what does that mean?
It's a mathematical domain. So we haven't tied it to geometry yet.
Okay, so we're just keeping it conceptual.
Yes, this isn't tied to geometry yet. It isn't tied to geometry yet, but we will get there when we basically take this domain and we map it to a element. Then it's mapped to geometry because that element can be fit to a specific geometry.
Okay.
So, yeah, you're jumping ahead. But right now, that's basically what this is going to be, the strong form for the weak form. When you look at the weak form, you're going to be like, huh, it's the same freaking thing, except you're throwing in these other variables. Well, it's because we're not defining these variables. And the way this works mathematically is you're going to make that value whatever you want it to be for it to be true. And there's horrible proofs that we can do to prove that. That's not for us today. But in general, that's the gist of strong form and weak form. But we're gonna play this out and keep going with it. But I just kind of wanted to have that little aside so you don't have to come to that realization on your own like 6 months after the class is over, like I did. Excuse me. So we have a domain. On the boundaries, so on these boundaries here, so remember we say on the boundary of omega, we would write something like that. And then interior and boundaries. So this is just notation. So if we're talking about in the interior of the domain and the endpoints, we would write something like omega bar. So this is equal to omega union boundaries. So it's omega plus the union of of the boundaries. So then we would write omega bar is equal to A, comma, B. So the point of this is you can see this in different forms. You can see omega is equal to parentheses A comma B. This is in between the endpoints. You can see this. Man,
sorry, real quick. Is it purposeful that there's a square bracket on the left side and a regular bracket on the curved bracket?
No, I was actually just going to point out that it's supposed to be a curved bracket when it's just the interior. It is squiggly brackets when it's just the boundaries. And it's, you should have a bar over the top, but if the bar is not present and you have square brackets, that means that you are including the boundaries.
Okay, cool.
Yeah, so interior, boundary, bowl. And if you were to see just square brackets signifies bowl. A little blurb about boundary conditions. Could be BC, could be BCS. Actually, I've seen it like this. BCS. If displacement is specified at a boundary point, it is known as a, I can't pronounce this, I'll spell it, DIRICHLET, Dirichlet, essential boundary condition. This is what it's commonly called, essential boundary condition. If the first derivative of displacement is specified, as a boundary point, it is known as a Newman, N-E-U-M-A-N-N, natural BC. So essential and natural are the common ways that you would, common terminology that you would see that. So we had labeled this section 1, I think, right? Yeah, so 1, 2-point boundary value problem. So that's about boundary value problems. So a little overview. The next thing is sets. And these are mathematical sets.
So real quick, if you had U1 specified as non-zero, that would mean one end is moving. Is that right?
What's that?
If you had U prime specified as a non-zero value, it'd mean that one boundary is moving. That boundary is moving.
It means there's a rate of change, yes. So a set, if we go back up, I think I wrote this up here. It's right here, the open set, A to B. So a set is a collection of elements or objects. So this is a real line numbers from negative infinity to infinity. This is a set of integers in. This is positive integers or natural numbers. Let me make sure I got this right. So in C, and C means subset. So n, the positive integers or natural integers, is a subset of all integers. So n is a subset of all elements or actually all elements of n are contained in 2. And Jacob, was that you that asked about the U prime?
Yeah.
You probably don't want to think of it as it's moving. You probably want to think of it as a string, because that's what we're ultimately talking about, right? You can have a strain rate without the system being moving. So you can have a nonlinear strain rate, and you're taking the derivative at a point, and the displacement's the same way. So we're defining displacements as functions of strain. So it's probably a better way of thinking of it rather than thinking of it as a velocity. Just think of it as a strain rate.
Okay.
Okay. I think this just might be confusing. No. Okay. So this is a little example here. So a function u of x, so displacement in x, this is our domain, and it's going to map to a range so in 2D, we're going to define our displacement in x as omega to our range. So let's call this x and y, I guess. That's an element. This coordinate here is 1, 1. Our domain is equal to 0 to 1. Actually, no, let's not call this y. Let's call both of these x. So we get 0 to 1, x, 0 to 1. So this is forced to be 0 to 1 squared. This corner down here is 0, 0. I guess I should have wrote that. So the plane so our range times our range in one direction times range in our other direction is forced to be this range squared. And all we wanted to that's there. We went over a lot of stuff with vectors. Have you guys heard about Hilbert spaces?
No.
Definitely not.
No.
I've heard of Hilbert's Hotel, his paradox.
Yeah, I don't think it's gonna add any value to what we're trying to get to here. Where we at? Okay, we'll just do this other one. So we are gonna skip number 3, vectors, because we spent a lot of time on vectors. And it's kind of repeated, just kind of in a little bit different fashion. So I'm just gonna say 3 vector stuff about mapping. We already kind of did that to death. 4 is called a linear vector, a function space. Linear vector function spaces. So to endow functions with geometric properties, such as norm, length, and angle, etc. Or even orthogonally. There's these things that have to be true. So let's go through them. I think before we start this, I want to put this side note aside for why this is important. Stems from the fact that solutions to boundary value problems like PDEs plus boundary conditions, they lie in certain function spaces. So this is stuff's going to be a little Greek. So the first one, L2 omega, or L squared omega, is space of square where we integrate functions in omega. So L2, how it's commonly referred to, is U, the integral over omega is U squared dx. It's less than infinity. So that has to be true. And I have a couple of examples here. So this is basically just a test to make sure that whatever your function is valid in the space, in the functional space. Let's write this as example 1. So very high level, U of x is equal to polynomials sines, cosines, exponentials, in omega is equal to our range. Example 2, U of x is equal to square root of x in 0 to 1. And the question you have to ask is, does U of x is it contained in your L2 domain. And so this is a check that you would do. Here's another one example where you have u of x is equal to 1 over root of x in 0 to 1. Then you'd have the integral from 0 to 1 over root x squared dx will give you a integral from 0 to 1 dx over x equal to 0 to 1 ln of x, which is equal to positive infinity. So, which is greater than. So this is a no-go. So therefore, u of x does not lie within your L2 domain. So it's just checks that you would do to make sure that your function is valid in your set or in your in your domain. So we define the L2 linear product of functions. F plus G, and that you guys have seen. F of G, L2 in omega is equal to the integral of omega F G dx. So this induces the norm to equal to the square root of f f 2 domain dx. So all this is really doing is go back to our potato, and we have tractions. Some of those are tractions equal to 0, so it's a fixed boundary condition. And we have other ones that are non-zero, so they're applied forces on our potato. And then let's say we have some body force, we have magnetic force in it. And remember our boundary value problem from elasticity that we're going to try to solve in finite element methods is it's the forces due to tractions plus the forces due to body forces. We're going to set that equal to 0 because we're in equilibrium. And we have to state that that function is valid within a certain domain. mathematical domain, right? We said it, you know, if we cut our potato, we said, okay, this is valid on this half of the potato and not on this half of the potato. So we're saying, okay, this is valid on this domain on the left side or the right side. And we have to do these little mathematical checks to make sure that those functions that we came up with work, that they're mathematically valid, especially when we map it over to the other half of the domain. So that's really what we're looking at. We have a function. We want to see if it works in the domain that we created it in as a kind of a quality check. But then ultimately, we want to say, okay, if it works in our domain that we defined it, we're going to force it to work in our other domain, and we're going to add these weight function things in there, which we'll get to. So we can say if it was valid in our original domain, therefore it's good in our good domain. I mean, in our new domain, and the new domain is where we're going to solve the problem. So, okay.
Hey, Professor, what's the word before the norm?
This induces the norm.
Induces. Okay, thank you.
Okay. And this Hilbert space thing is the next step in this. So Hilbert spaces. So this is the next level of checks that you have to do, and this is HK in our domain. And our displacement field is contained in our Hilbert space in omega if displacements contained in L2 omega, if the first derivative of our displacements are contained in our L2 space, if our second derivative of displacements are valid in our L2 space to UK. So what this means is if our K is equal to 2, we would have H2 and omega, and we would have to check this, this, and this. We would not have to check, you know, the UK is number 2. So H0 is equal to our L2. They're one and the same. The first one here. So so the first thing that we check is this. So this is, maybe let's say this is 1. So check if that's true. And then our second thing that we're going to verify is displacement in x equal to the square root of x, u of x contained in L2 omega is equal to H0 does our displacement field live within H1 So you start with K equals to 0, and we already did that. Then look at k equals 1. So displacement lives 10 L2 omega. We did that one. And U prime and then L2 omega. This one is a question mark. That one we already did. So U prime of x is equal to 1 over 2x square root of x was not contained. L2. Or our U of x contained H0. But U x was not contained in H1. So this one is a bust. Then we look at U of x is equal to the absolute value of x and minus 1 to 1. So this is okay. U of x. So we have positive x if 0 is less than x is greater than or equal to 1. Negative x if negative 1 is less than x less than or equal to 0. So you're looking for U of x contained in H1. So that's a verification that do. So that's Hilbert space. You basically just have to check the derivatives. So whatever your function is, you check the derivatives up to whatever that k value is for your problem. It's usually for the stuff that we're doing, you have to go to the first derivative for linear elasticity. So 2 Hilbert space, we're going to go to 3 now. This is space of continuity. Oh, sorry, of space of continuously differentiable functions. This is C to the K within omega. If U is contained C, K, omega, then U is continuous in omega. And this applies for U prime, U double prime, UK. So all polynomials sine, cosine, functions are in C infinity omega or any omega. So here's an example. So we're trying to find the highest derivative that it's continuous. So we have U of x is equal to minus 2x squared, 3x to the 4th. So this x is less than 0. This x is greater than or equal to 0. So this is continuous. So you're good there. This U of x minus 4x, 12x third. This x is less than 0. This one is greater than or equal to 0. This
Did you write the prime on above the U?
Continuous. Yep, that's U prime. And then we check U double prime. And that is minus 4. 36x squared. And this is x is less than 0 and x is greater than or equal to 0. And this particular one is not continuous at x equals 0. So this is a no-go. That means that our highest derivative was U prime. So therefore, we can state U of x is contained within C1 omega. So you keep taking the derivative, and then whatever your highest derivative is that's continuous, that's the C that you can choose. So now a more formal definition. Space. Let x be a linear vector function space then the following must be true. One, alpha u plus beta v is contained in X for all alpha, beta contained in our range and u, v contained in X two, 0 is contained in X. 3, associative and distributive laws. Hold. Let V equal our displacement field, U contained in our Hilbert 1 space over domain, over our domain of with 0, 0 equal to 0. Where omega is equal to 0 to 1. And remember this omega, this is just interior, right? So this is the formal notation of a linear vector function space. Linear vector function space. So as we move forward, like on Tuesday, and we're talking about the next step for this, I think we're probably going to do like a 1D elasticity problem. When we look at those functions, when we look at that first equation, the boundary value problem, it assumes that you went through and did all these checks and balances. That all of this mathematical stuff has already been sorted out, and that you know that you have a valid space, your highest, you know what your highest derivative is that's continuous of your C space. It's typically the first derivative has to be continuous, and that kind of makes sense, right? What would that mean? So displacement is essentially strain, right? And if we take the derivative of our displacement field and it's non-continuous, what would that mean from a physical perspective of your part?
It broke?
Yeah. you have a discontinuous strain field. It has a hole in it. It broke. Something's going on. So I think from an engineering perspective, yeah, it's busted, man. It doesn't work. But from a mathematical perspective, your solutions, something's wrong, right? Something's wrong. You either have a bad function to begin with, you have a bad boundary condition, maybe you forgot a boundary condition. It's kind of a telltale sign that something's up. You can't trust the results of whatever you're going to get. So you have to make sure that your H1, your Hilbert space, or your C, that you'll typically hear people ask, is it C1 continuous? And that's what they're talking about is the first derivative of your displacement field, of your displacement function, is it continuous? Is there a hole in it? Is it have a Kronecker delta? Does it shoot to infinity, at some spot? So it's part of the check and balance process. So it's assumed when we move forward, we do any problems or anything like that, the assumption is you've already done this work that we went over today. Okay. Any questions? Sorry, we're a minute over. No?
So you had everything labeled 1, 2, 3, 4 in the subsections. So was the 1, 2, 3, and 4, or those were all checks that you run through?
Yeah. Yeah. Any more questions?
Oh, sorry. One unrelated question to this. Does Whiteboard let you export a picture in higher resolution? Because a lot of the exported notes were kind of too fuzzy to really kind of see what was going on. Because
it's because they're too long.
Yeah, well, I mean, they're not too long if you can export in a higher resolution, but if you couldn't, then they'd be too long. Yeah.
That's the only option to export it is the PNG.
Okay.
Did you want these from today?
Sure.
What is today? Okay. Any more questions?